Okay, so hi everyone. We're going to work on rational functions today, rational functions. And rational functions refer to really fractions. And we don't like fractions in general because it's just, in my brain, it's harder than regular easy numbers, right? 1 is so much easier than 1/2, all right? So, and adding fractions is quite terrible, and we'll work on that later. But what we're doing with today is we're going to learn on characteristics of how to graph fractions. And these fractions meaning these functions that have an x on the bottom. X on the top is not a big deal, but x on the bottom is a big deal. So let's look at our first one, and we're going to say 1 over x. That's our easiest one for us to look at. And we're reminded that whenever I'm looking at a function, we'll call this f of x, we think about what numbers would work. And you can start plugging in numbers in here. And let me create a table here. I'll call x and y. Remember, f of x is the same as y. If I plug in -2, -1, 0, 1, and 2. We're going to plug in 5 numbers here. I want to try to figure out what does this graph kind of look like. Now, plugging 5 numbers already, to me, is a lot of work. If this equation was harder, it would take me a lot of work here. And the goal, just like in our previous way of graphing large order polynomials, is to not do a lot of work, looking at special characteristics so that we can just plot a few points that will give us a picture of what the graph should look like. Okay, and that's our goal. Do as little bit of work possible to get a graph that makes sense. So this first part, let's go ahead and plug in -2. So 1 over -2, 1 over -1, 1 over 0, 1 over 1, and 1 over 2. Okay, so we're plugging that in. We see I'm gonna write these as decimal numbers. 1 over 2 is -0.5. 1 over 1 is 1, so -1. We have, we're dividing by 0. I'll come back to that in just a moment. 1 divided by 1 is 1, and 1 divided by 2 is 0.5. So the one I skipped here was 1 divided by 0, and we're going to call that undefined. Undefined. And we'll come back to that in just a little bit. But we're going to say undefined because traditionally when we learn in Algebra 1, when you divide by 0, you can't divide by 0. It's impossible to divide by 0. And we made this fancy word called undefined. And that's actually one of the only parts that we have struggled with. We cannot divide by 0. And another one from Algebra 2 is we can't take square root of negatives. These are the only 2 points that really mess us up. Is we cannot divide by 0, which is what we did here. And then we cannot take a square root of negatives. Every other time, all our numbers are always really cool, and we can solve for that. Okay, so let's go ahead and graph this. I'm going to draw this in x and y scale. Here's my x, and here's my y. And 1, 2, -1, -2. And we'll draw this at 1 and -1. Okay, so at 1, positive 1, we're at positive 1. At 2, though, we are at 1/2. On my left-hand side, at -1, we are at -1. At -2, we are at -0.5. Let me actually switch colors here so I guess I can probably see a little better. Okay. So how will this graph look? There's a couple of options that using the graphs that using the points that we have. Now, this is wrong, okay? So let's say okay, this is not the graph that we're talking about, okay? And there's a couple reasons why. Now, if I plug in more points, such as, what if I write x is -3? Oh, x is 3. If x is -3, we have 1/3. If x is 4, we have 1/4. If x is 5, we have 1/5. If x is 6, is 1/6. If x is 7, 1/7. Is the number getting bigger or smaller? 1/4, 1/5, 1/6, 1/7, 1/10, 1/100, 1/1000, okay? So as x gets bigger, look at the y values. As the denominator gets overly swollen, it gets bigger. My number gets smaller. So what does this look like? It looks like this graph is getting closer to 0, and it's going to eventually not touch 0, but get darn close to 0. The reason is, what is 1 divided by 1,000,000? Is that a big number or small number? That's a really small number. It is not 0, but it is pretty darn close to 0. And this is what we're going to call a horizontal asymptote. And we'll talk about that a little bit later. It's a number that we're going to trend to in the horizontal direction. We're going to get close to 0, but we're not going to actually touch it. Now, what happens on the left side if I put -3, -4, -5, -6? If I do that on the left side, we end up with the same pattern. The number gets smaller, but in a negative way. So we said this was -1, -1.5, -1/3, -1/4, -1/5. As you can see, these numbers are getting smaller, but they're on the negative side. Will this ever touch 0? Again, the answer is no. This will never touch 0. Now, what happens in this middle part here? What happens in this middle part here? Are these lines going to connect? And let me go ahead and start pointing out the trend of what will happen. If I plugged in 1 over 0.5, right, isn't 0.5 right in the middle here? What happens at 1 over 0.25, even closer to 0? What happens at 1 over 0.1, even closer to 0? As we approach 0 from the right-hand side, as we get closer to 0, what happens to my y value? Now, I want you guys to be able to do this in your head, and not to overthink it. We're going to think of this as money. How many 50 cents are in a dollar? There are 2. So 1 divided by 0.5 is actually 2, because there are 2 50 cents in a dollar. How many quarters are in a dollar? Right? Isn't 0.25 like a quarter? How many quarters are in a dollar? That's 4. How many dimes are in a dollar? That is 10. So I want you guys to realize this thing about fractions. If I divide by a large number, my answer gets smaller. But if I divide by a small number, my answer gets bigger. I want you guys to notice that right now. If I divide by a big number, my answer gets smaller. Means you have to share more with your family members. Okay. Imagine if you had one sibling. 1 divided by 2. That means you get half the stuff. That sucks. But what if there are 4 siblings? 1 divided by 4. You get a quarter of the stuff. Man, more kids means less for you. But if I divide by a small number, okay, 1 divided by a small number means I'm going to get a big result. Because how many small numbers, how many 0.5s are in 1? 2. How many quarters are in 1? 4. How many tenths are in 1? 10. So the idea is as x gets smaller towards 0, our y value is going to rocket ship up. And this is what happens. It shoots up and it's going to head toward infinity. If I went ahead and put negative signs on all these problems, take a look here. If I just visually put negative signs on all these, all my answers will become negative now. So on the left-hand side, our answers will look like negatives. And this is the graph of a rational function. Rational functions will have values that do not work, like 0 here. If we divide by 0, we end up with what we're going to call right now a vertical asymptote. And that's how we're going to start off this conversation. If we divide by 0, no, we can't divide by 0. We call that undefined. And we are going to shoot off to the moon. We're going to shoot off to infinity or negative infinity, depending on which direction we're headed. Now, I'm going to go ahead and talk about this big idea in just a moment. But vertical asymptotes are just when the denominator is 0. Okay, denominator is 0. That's where our vertical asymptotes are going to happen. We're going to have an excuse out of this a little bit later. But right now, let's just take it as that. If we divide by 0, that's going to be a vertical asymptote for us. That will not always 100% be the case, but we'll change that rule once we get there. Next thing, these graphs have a horizontal asymptote, and we'll come up with a rule for that next class. I'll tell you guys how to discover these horizontal asymptotes. But so far, take a look here. This one is going to be 0, and we are also going to get stuck at 0 over here. So we have a couple things that we want to make sure we pay attention to. We have vertical asymptotes, and then we also have horizontal asymptotes. And this defines my graph. This will help me lay out the structure of my graph. So today we're going to describe how to find out vertical asymptotes. Now, to go back and discover what we talked about before, why can't I divide by 0? And why do we call it undefined? What does undefined mean? Mr. Cole, that sounds like my last relationship. It's undefined. You're hanging out for a couple months and you're chilling together. And are you guys dating? It's undefined. We haven't talked about it yet. You guys have been hanging out for a couple months. Well, he hasn't said anything. Well, she hasn't said anything. It's undefined. Awkward, right? Sounds like. Sorry. It sounds like you're being played, right? Yeah. Okay. So let's talk about why it's undefined. Now, so here is the reason why. If I go ahead and I mentioned before, if I divide by 0.5, we end up with, okay, 0.5 is a small number and 0 is a very small number, okay? So if I divide by 0.5, we end up with 2. If I divide by 0.25, a smaller number, we end up with a bigger answer. If I divide by even a smaller number than that, 10 cents, 50 cents, 25 cents, 10 cents. How many 10 cents are in a dollar? We end up with 10. How many pennies are in a dollar? Whoops. How many pennies are in a dollar? That's 100. Well, how many thousandths? And if you can see, 0.5 to 0.25, 0.25 to 0.1, 0.1 to 0.01, 0.01 to 0.001. We're getting closer to 0. Because we already said 0 doesn't work, we're just trying to see, by experimentation here, what would it look like as I got closer to 0. Our value is at 1,000 already. Do you guys want to graph 1,000? Do you guys want to graph literally 1,000? No. So we draw this arrow saying that, you know what? It's 1,000. So we're going to draw this arrow shooting up to infinity. And that's what 1 over 0 is. Now I'm going to write this in a calculus way that we're going to learn a little bit later. The limit as x approaches 0, as the graph approaches 0, and that's the idea of a limit, it's what does it look like if I could get there. As this graph goes to 0 of 1 over x, meaning if this becomes 1 over 0, what does the graph look like? This looks like infinity. It isn't infinity because infinity isn't a number. And that's why we call it undefined. It's undefined because we can't get there. Infinity is not a value we can reach. We can get to Mars. We can get to Saturn eventually. We can get to the end of the solar system. But can we get to infinity? Nope. When are you going to get there? I don't know. It's undefined. It's not within my comprehension. How's your relationship? Well, it's undefined. Why? It's infinite. It doesn't exist. It's made up. And this is the idea of infinity. It's a concept that we use in math to describe keep on going. All right? There's no cap on that. Okay. So I'm going to describe this using another example of cake. Here is my cake. I'm going to draw this birthday cake. It was my birthday a little while ago. I don't like celebrating my birthday too much. I turned 40 recently, so I'm probably the age of some of your parents. And so I'm going to draw my little cake here. Okay. I feel this looks a little off, but oh well, this is my cake. All right, so I'm going to give my cake a little decoration. All right, Asian cakes are the best. Okay. Happy birthday to Mr. Ko. Okay. All right. So I'm going to ask you a question. How big of a slice of cake do you want? And instead of saying like a little piece or a big piece, we're going to use this example of saying, I want half. Wait, how much cake do you want? You want half? What the crap? So I listen to you and you say you want half. So I cut the cake in half. So if I cut the cake in half, 1 divided by 0.5, I can come up with 2 slices, right? Make sense? I can come up with 2 slices. What if I say I want a quarter of the cake as a slice? Fine. Thank you. What if I give you a quarter? Fine. I cut the cake into quarters. Take a look at these long quarters. That means you end up with 1 over 0.25. You end up with 4 slices. Are you guys kind of okay with this? The idea of slicing the cake? Hopefully it makes sense. Now what happens if I need more cake? I need to cut smaller slices. So you say, Mr. Ko, give me a smaller slice. So fine. 1 over 1 over 0.10. Okay, 1 over 0.10. So let's cut the cake into 0.10. I'm sorry, I need to delete that. we're going to cut the cake into 0.10. Here we go. Unfortunately, I have to cut this cake into a bunch of tiny slices now. So let's pretend these are 9 slices. 9 cuts means 10 slices, right? So you can tell that if I cut smaller slices, you end up with more cake. Now, what if, and it's probably your dad, he says, I want a slice of 0. Okay, I want a slice size of 0. Fine, here's your slice of 0. Nothing. How many slices can I come up with now? The slices are so small, it's nothing, right? How many slices do I have? I have infinity. I have enough to share with everyone because I'm giving them nothing. Or essentially, it's so small, it's practically nothing. So how much can I share? I can share to everyone in the universe because I'll never lose cake because I'm sharing nothing. The slices are so small, I can fill the world with no slices. And that's the idea. If I divide by 1 divided by 0, we really are saying infinity. How many zeros are in 1? As many as you want. You're never taking it away. So, as our graphs get closer to a 0, now let me give you another example. If I say x plus 1 here, this is my function. What is the 0 on the denominator of this graph? We can say x plus 1, whoops, x plus 1 is equal to 0 when x equals to negative 1, right? That's our classic way of solving in algebra. So, can the graph actually be negative 1? Can x be negative 1? Nope, x cannot be negative 1. And that's our point. We're looking for values that this would not work at. If x was negative 1, we would be dividing by negative 1 plus 1 is 0. And this leads me to say infinity. That's what we're really saying. This graph is going to shoot to infinity. It's going to go to the moon. And this leads us to say this is a vertical asymptote. It's a vertical asymptote. So on a graph, this is what I would automatically start drawing. I would draw my graph like I normally would. I would label first the vertical asymptote. What graphs am I not allowed to play on? Right? When you go to a friend's house, you don't just randomly walk into every single room, right? There's a couple norms. First thing is you go to the living room and you stay there. And if your friend says, yeah, make this your home. So are you going to start really wandering in everyone's room? No. Right? There's some norms going on. And the thing is, it's because your parents taught you right. You don't just randomly roam around in someone's house. But you might have some friends who just come over and just do what they want. So at negative 1, we automatically know that we're not allowed to be here. So what I'm going to do, so take a look, everyone. This is what I ask you to do when you guys are drawing these, is draw a dashed line. And this reminds me, get off my lawn. It says, stay away from this. Okay, that's it. We're not allowed to graph that. We're going to take a Fast and the Furious jump over that point. It's not going to exist. Okay, so now the next part is, how does this graph look? I'm going to tell you right now the horizontal asymptote for this graph, HA, horizontal asymptote, is going to be y is equal to 0. I'm going to tell you that right now. We'll figure out more about that later. And I'll teach you guys how to do that. It's actually very simple to figure it out. So I'm going to draw another dashed line here for my horizontal asymptote. Now, this is the part that you want to notice now. We have 4 possibilities to graph on. We can graph up here. We can graph down here. We can graph over here. Or we can graph up here. Okay. And why did I pick these 4 spots? And take a look here. I went all the way up to the line. I'm going to go all the way up to the line. But I'm going to leave the line out because you're not allowed to touch it. If you guys play basketball, when you touch the line on the basketball, are you in or out? You're out, right? You're not allowed to touch that line. That line is not part of the game. You touch it, you're out of the domain. So this is what we're going to do. And it's very simple now. Now that we drew our, in a sense, our borders for our graph, we decide, am I going to be up here or down here? And the way we do that is just pick an easy number on the right side. Pick a number on the right side of negative 1. Pick a number on the right side of negative 1. Let's pick 0. So if I plug f of 0 in, that's 1 over 0 plus 1 is 1. Great. At 0, your graph is 1. Okay, this leads us to say the graph is 1. Well, if the graph is 1, here's the cool part. I can automatically say the graph looks like this. That's it. That's how much work you need. I trapped you in the right-hand corner. You're going to make that right-hand corner your home. Now, why is it curved? Why is it so curved? Now, if I had drawn a point like this, is that allowed? Didn't we say this graph shoots up to infinity? Because I'm not allowed to be here, right? So it's almost like me putting a piece of paper or a piece of cardboard on a corner at my house, a corner of a room. And what happens if I press the cardboard in, it bends out and it flattens out. Because the horizontal asymptote is a wall, the vertical asymptote is a wall, and we're not going to cross that. Oh, that's weird. We're not going to cross that, so it makes this curve-like surface. On the right side, we're going to eventually, from this point, we're going to head towards 0. See, we're going to head towards 0. And from the point going up, we're not going to cross it. We're going to shoot off to infinity. Because as we get closer to the graph, our denominator gets smaller, and that leads us to a larger y value. Let's look on the left side. Pick a number that's less than -1. Maybe -2? Sure, let's pick -2. F of -2. If I plug in -2 to my function, 1 over -2 plus 1 is 1 over -1. Hey, -1 divided by -1 is -1. And we're going to be right here where I wrote the -2. That's right, -2 on top. All right, so is that what the graph looks like? Nope, remember we said we're stuck at this wall here. We're stuck at the vertical asymptote, and we're stuck at the horizontal asymptote. So we're stuck in that corner. Let's go ahead and continue this corner. And that's what the graph looks like. To verify this, just to show you guys on Desmos. Desmos, again, is always a great resource. The goal isn't for you guys to use Desmos to escape from understanding how to graph, but it's a nice way to check it. Now I'm going to graph this graph as 1 divided by x minus 1. Oh, x plus 1, I'm sorry. And look at their graph and look at my graph. I would say that's pretty on point. That's pretty darn good for the amount of work I put in. So I'm going to graph another graph very similar to this, and then we'll graph something even more fancy than this. Now, we want to talk about one more thing when we're discussing the graph, which will be on your homework. They're going to ask you, what is the domain? And the domain is our x values, okay? What x values am I allowed to use? Were we allowed to find x at 0? Yes. How about x at 1? Yes. X at 2? Yes. X at 3? Can I go all the way to infinity? Yeah, sure. How about on the negative side? -2, -3, -4, -5, -6? Yeah, we can find all these values and we can find a related y value. But what value were we not allowed to use? We weren't allowed to use 0. And that's the thing about domain. Domain says, hey, we get this game. What values can we use and what values can we not use? Well, you can use anything you want except 0. So there's going to be a couple different ways of writing this. We can use this double R symbol, being all real numbers, right? Except for x equals to 0. Or we can say, oh, sorry, all real numbers. X equals to all real numbers except x cannot be 0, right? That's almost like an English way of writing it. Now, we're going to look at this using our parentheses notation. So to write this, if I say negative infinity, comma, to infinity, when I write it this way, that means you can have from negative infinity to infinity, you can use any number you want, including 0, all numbers in between. When you see a notation like this, that means negative infinity to infinity. We use the parentheses to denote, are we going to include or exclude the number? So we use a parentheses usually for infinity because we don't want to include that number. Now, if I write this from 0 to 2, that means the graph is only allowed from 0 to 2, solid to solid. If I write from parentheses 0 to 2, this means I'm allowed to include 2, but not include 0. Do you guys remember these types of notation from Algebra 1? If I use bracket 0, comma 2, that means you are allowed to include 0, but not include 2. So the way we refer to these is looking at these, this system is that I can use every number from 0 all the way to 2, but don't include 0. That's why it's hollow. Up here, you can include numbers from 0 to 2, 0, 1, 2, any decimals in between. That's totally fine. That's fine, Katrina. And on this bottom, I can all numbers from 0 to 2, 0.1, 0.2, 0.3, 0.4, 0.5, but don't include 2, but you're allowed to include 0. Okay, so this is just a quick way of looking at it. Our last problem, I'm going to give you guys two graphs here, and we're going to talk about the domain of the two graphs that we just wrote. We said 1 over x, and the graph looked like this, where 0, x was not allowed to be 0. Our second graph was 1 over x plus 1. We said we were not allowed to be on -1. So we're going to talk about the domain for these two graphs, and hopefully you can catch that it's not super hard to do, not at all. So the domain, what x values I'm allowed on the left side here. So on My Open Math, when you're clicking on it, there'll be a parentheses symbol, so please click that. Parentheses first. We're allowed to play on the left side. See, we're allowed to play on the left side. So we go from -infinity and stop at 0. We are not allowed to include 0 in the problem. Then from 0, we hop back on, and then we go to infinity. It's almost like riding a bus. Sometimes you got to get off and get back on a different bus at the same stop. Or maybe you might cross the street. But if you're taking a bus usually doesn't take you from point A to exactly where you want to go, point B. You have to make a stop and switch buses sometimes. So I'm on my bus from -infinity to 0, stop, get off the bus, and then hop back on from 0 to infinity. We're going to include a U symbol here. That means this idea, the idea of union. So this is OR. So we're in area A or area B. This is where the graph exists. How does this domain change for our next problem? We said we weren't allowed to be at x cannot be -1, right? But are we allowed to use every other point? Yeah. So this graph goes from -infinity, but our first stop is at -1. Stop and get off. Then we get back on the right side of the graph at -1, and we can proceed to the end of the graph, infinity. And these are x values. What x values are we allowed to use? I'm going to use union also, because it's, again, A. I can play in area A or area B. We're going to look at this idea of domain one more time as we look at our next problem, and this is going to be our last example today. The example is going to be 1 over x minus 1 and x plus 2. Now, this is my function here, and I have more than one value that I'm not allowed to have, because then we would be dividing by 0. If you look at our denominator, what are the zeros of this graph? The 0 on the denominator would be 1 and -2. I hope you guys can see that as 1 and -2. Because if I plug in 1, we end up dividing by 0. If I plug in -2, we would be ending up dividing by 0. -2 plus 2 is 0. 1 divided by 0 times anything, that would be 0. Okay, so we're not allowed to have these points. So on our graphing points, I would always graph our vertical asymptote first, like I mentioned before. X is 1. 1, 1, 1, 1, 1. Up, don't, you remember, you're not allowed to touch that. Don't touch it. And -2. line, 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 line. I'm going to tell you guys myself that the horizontal asymptote is y is equal to 0. I know that automatically because it's a rule that I'm going to teach you guys next time. It's super fast to find. Here's my horizontal asymptote. Now, I want you guys to see that I get to play on the left, in between, and on the right. What separates this graph? It's my two rivers, my two vertical asymptotes at -2 and +1. Why? Because if I did plug in +1, we would be dividing by 0. Does not exist. The graph is going to go to infinity. If I plug in -2, the graph doesn't exist. We divide by 0. We're going to infinity again. Now, how do I figure out how to graph? Am I going to be on top or on bottom? On top or on bottom? On top or on bottom? And the way we do that is just by plugging values in. So on the right side, pick a number bigger than 1. Remember 1 is my last root on the right, on my last vertical asymptote. Pick a number like 2. So we plug in 2 into the problem. F of 2 is equal to 1 over 2 minus 1 and 2 plus 2. Yes, you're going to do a little bit of math here, but 2 minus 1 is 1, so 1 over 4. Is this on top or on bottom? This is on top, so this is how much I graph. Did I even try to get too close? Did I even try to get to 1/4? No. We're just trying to figure out, am I going to be on top or on bottom on the right side? And since I'm stuck on top, I'm going to be stuck by the vertical asymptote and the horizontal. So we got to bend that line to fit. That's all we have to do. If you want, you can plug in more points. You can plug in 3, 4, 5, 6, and you'll see that the number will get closer to 0. We're stuck in that corner. We're never going to jump to the bottom in this problem. We will have problems later that we will jump, and we'll see obviously why it's going to jump later. Okay, let's pick a number on the left side. That's -3. Fine, let's plug in -3. F -3. 1 over -3 minus 1 and -3 plus 2. Okay, this gives us 1 over -4 times -1. Hey, negative is a positive. We're back on top. So on the left-hand side, we're going to be on top here. How do I know it's curved? Again, it's because of the vertical asymptotes. If I try to draw a line like that, we know we're going to get blocked off. It's going to bend it up. We know a horizontal asymptote is going to bend it down, or bend it over to make it go to 0. So we're going to be stuck in that corner. Oops. We're going to be stuck in this corner. And we said we're going to be on top. Okay, what happens in this middle realm? Are we just going to cross over? Now there is a rule for us. Remember, if we're ever going to cross through 0, we have to have a 0 in the numerator. And in this case, it will not be 0 because 1 is never equal to 0. That's a fancy rule. We'll talk more about it later. But I know I'm going to be either stuck on top or on bottom because I'm not allowed to cross through the border here. There is no breaking through the ice. So we'll pick a point. Let's plug a point in between. 0 is in between, isn't it? Let's plug in 0. So that's 1 over 0 minus 1 and 0 plus 2. That's 1 over -1 and 2. That's -1/2. Oh my gosh, you guys see how that's negative? So we are stuck on the bottom of the graph. Let's go ahead and verify this using Desmos. And I'm going to tell you, this is going to look pretty convincing, okay? We said we're going to have x minus 1 and x, oh darn it, it didn't go through. X minus 1, close parentheses, and x plus 2. I want you to take a look at their graph and look at my graph. And aren't they pretty darn close for the amount of work I did? And the reason why this seemed to take a little while is because I was talking through this the whole time. Once you guys get good at this, you can graph this equation in about a minute. I'm not kidding, about a minute to get to what we see on the right. That's pretty good, isn't it? For the amount of work that we did. We plugged in 3 points, and the only reason why it took so long because I wrote out all the work. And just like graphing large order polynomials, we have tips and tricks to graph rational functions. Now, the last part here is what we need to take a look at is my domain. So looking at the graph, what is the domain? I'm going to erase this little spot here. Actually, no, let me draw this again real quick for you guys so you guys can see it. You guys don't need to draw it over again. But we said -2, 1, and then we said the graph goes something like this, something like that. So I got rid of the x-axis so it doesn't confuse us. I got rid of the x-axis, but I will write 0 here, okay? So it doesn't confuse us. We have 3 parts of the graph. We have the left part, which goes forever. We have the right part, which goes forever. And then we're stuck in this twilight zone area right in the middle. So these are the 3 domains we have to label. So let's go on the left side. We go from -infinity to, what's my first stopping point? We go -infinity. I'm taking a train, I'm taking a bus. First thing I need to stop off at is at -2. I get off my bus, I cross the street, and I hop on at -2. I take -2 all the way to, where's my next stop I have to get off at? Get off at 1. So I go from -2 to 1. And we express these, it's not an XY point. This is a beginning and the end. I'm starting at -2, and I'm going to go all the way to 1. And then I'm going to get off my bus, hop back on across the street, and then ride the rest to heaven from 1 to infinity. So this is the domain. These are the values I'm allowed to use. I'm going to use a union to say, hey, it's this or this or this. I can be in any of these 3 areas, and these will give me a y answer on the graph. The x values cannot be at -2, and they cannot be at 1. But the domain is illustrated in this form here. Okay, that's it.